Welcome to the RCF Applied AI Seminar Series. Today I'm going to be talking about explainable AI for healthcare applications. Explainable AI is important because it helps clarify AI decisions. It builds trust amongst clinicians and patients. It's also very important for safety considerations. It helps us identify and correct potential biases or errors within models, ensuring reliable interventions. It's also good for compliance. Typically, we need to show that our models are actually learning the correct things. Explainable AI meets regulatory standards, requiring transparency and accountability, aiding approvals and integration. In terms of collaboration, it fosters better collaboration between clinicians and patients, helping the patient to understand that the model that is being used by the clinician is indeed learning the correct things, and it gives a sense of accountability and trust. Explainable AI is extremely important for any AI model that's being used in production. Part of this involves peeking into the black box. Integrated gradients and feature ablation are some tools that are being used to identify feature importance across modalities. In addition, layer activation and layer attributions are important for understanding how specific layers contribute to model decisions. This is crucial for imaging-based models. Saliency maps are also very important for visualizing which parts of the input influence the model's predictions. Comparing across different models helps us understand how different architectures process and prioritize information. These techniques are customizable and extensible to some extent. So they allow us to change the model to better learn the appropriate parameters. Today, I'm going to feature a couple of algorithms that are part of the CAPTM library. So this is a library that can be used within PyTorch and within TensorFlow to explain different types of models and what they're actually learning. So this is a selection of different attribution algorithms that are available via CAPTM, and the underlying method that's being used, whether that's a gradient-based method, perturbation-based method, or another type of method. These algorithms are very useful for examining your models and determining what the model is actually learning. This figure is a little bit small, but I'll send out these slides so that people will have the ability to see this. There's different types of models which have different use cases, and they have pros and cons. So there's SHAP-based method, gradient-based methods, saliency, occlusion, guided back propagation and deconvolution, RADCAM, layer activation, noise tunnel, etc. And I have here in this table just kind of a description of some of the pros and cons of these different algorithms and where they should be used. Some of these are computationally intensive. Some of the most commonly used would be SHAP-based methods, occlusion, integrated gradients, and saliency. So those would be most often seen in different publications. Today, I'm going to highlight on occlusion and integrated gradients within the code demo. Let me just introduce integrated gradients. It's an attribution method that helps explain the predictions of deep neural networks. It assigns importance scores to input features based on their contribution to the model's output. In the case of imaging, we typically can visualize these attributions. So we can see which parts of an image are contributing most to a classification. Gradient-based methods are important for understanding which pixel-based features are contributing most to a classification decision. So how does this actually work? We apply this to an already trained model. We load the CNN model, we load the input image, we define a baseline, and we zero the image. We interpolate between the baseline and the input, and we compute the gradients between those points. We can then use those integrated gradients to calculate an attribution score, and then we can visualize those. This requires selecting a baseline, computing a gradient, doing a path integration, and then visualizing the attribution. It's a gradient-based method that is reliant on a baseline. Occlusion is another method that I'll be demonstrating. So occlusion is a method for interpreting neural network predictions by systemically masking parts of the input and observing the changes in the output. So you typically utilize a sliding window that occludes parts of the image, and we can see how it affects the output. So this helps determine the importance of different regions in an input image for the model's decision making. It utilizes a sliding window, replaces that with a baseline, and calculates the attribution. This is how it works. Again, we're utilizing an already trained model. We load the input image, we define the occlusion window size, we slide the window across the image, we replace the section with the baseline, run forward pass with the occluded image, we calculate the output difference, and we aggregate differences for the attribution scores, and then we can visualize the attributions. So I'm going to jump into an example. I've utilized this example previously for demonstrating how to train a CNN. So this is a good starter code for understanding how to pull some data, how to take an off-the-shelf CNN like ResNet 18 and actually utilize it. We apply some data transforms to basically normalize and take random resize crops of the train and test set images. We create an image-based data set and a data loader. We have defined classes. This model is learning the difference between normal lung CT versus pneumonia. And we can see some examples of normal versus pneumonia. We define the training loop. So here we define how we want to train the model. We have a for loop, which iterates over epochs and which iterates over batches of data. And based on how the model performs in the test phase, if the loss decreases, then we create a new copy of the model. Basically, we're doing checkpointing to make sure that we capture the best model as in the training phase. And then we can also visualize the outputs of the model. The code will be available to everyone via the GitHub. We trained the model and the best test accuracy was 87%. It's able to learn the difference between pneumonia CT and normal CT with a fairly high degree of accuracy. However, there's some mispredictions. We can use CAPTUM. We can use CAPTUM to visualize the attributions like the pixels that are contributing to the classification. So this is just a loaded pneumonia image with a score associated. So it's 86% sure that this is pneumonia, and the actual label is indeed pneumonia. But we can utilize integrated gradients to look at what the model actually learned. Based on this image, the model is actually learning is mostly related to the spine area, with some areas in the lung being shaded. The model did not learn the correct features, even though it has a fairly high accuracy score. So this can be improved by training the model for a longer period of time or revising the model architecture, adding new data to the training set. So I'm also utilizing occlusion. So this is the other method which I described. And you can see the original image. You can see positive attributions that are contributing to the classification of pneumonia and negative attributions. The negative attributions would probably be what I would be looking for. It's learning the spine region and this dark region. It learned some true features, although there's some negative attribution features that I think may need to be included. The model probably needs to be trained a little bit more and potentially with more data. So this is a very powerful and simple to use method if you are already utilizing a CNN. That's all that I have in terms of slides. If anybody has questions, I would be happy to answer them. If you'd like to schedule time with me, scan this QR code and we can discuss any projects that you might have where you might want some expert consultation or otherwise port them to run on a supercomputer. This seminar series is being run by the Center for High Performance Computing from the RCIF, and we're looking to add more people to our cluster. Happy to take a call with anybody who would be interested in utilizing our high performance computing services. If there's any questions, I'd be happy to take them now. The 86% accuracy is based on how the model performs on the test set, where we know what the true versus predicted labels are. It is in agreement with human diagnosis because the labels are coming from human labelers. 86% accuracy on the test set would be in agreement with human labeling. Are there any other questions? How to get the character from disease images. If you mean classification, you would have your own labeled data. So that would require having a labeled data set that you use to train a model. There's different ways that labels can be assigned, either by a human expert or utilizing unsupervised methods to determine whether there's clusters of data and then assigning labels that way. But the best method would be to utilize human-based labeling from an expert. Let me find the GitHub repo. So everybody will have access to these codes and the slides via the GitHub repo. Any other questions? If not, I think we'll close the session and I'll be sending out an email with additional information. Thank you.